Hello, my name is Christopher. Today I'm presenting a paper titled Program Feature-Based Benchmarking for Fuzz Testing. It was published at ISSTA in 2025, and it's by Miao, Kumita, Bowden, and Wei. Before we look at the exact methodology of the paper, I'm going to spend a good amount of time going over the background. The goal of this presentation isn't just to summarize one paper, but to use this paper to explain a broader problem in software security. In the security industry, we rely heavily on automated tools to find vulnerabilities. But that raises a fundamental question. How do we accurately evaluate the tools that we are supposed to evaluate our code with? If you build a tool to find bugs, how do you mathematically prove your tool is better than existing ones? Today, we're going to cover what fuzz testing is, how the mechanics of modern fuzzing work under the hood, and how we currently benchmark these tools. Then, I'll explain why the current evaluation methods are deeply flawed. After that, we'll look at the solution this paper proposes, which is a new benchmarking framework called Feature Bench. Finally, we'll discuss the actual results of their tests and the limitations of their approach. To understand the paper, we first need to understand the tool it evaluates. What is fuzzing? When a developer writes a piece of software, they write tests for it. But manual testing is inherently biased. A developer will input the data they expect the program to receive. If a program asks for a date, they will type a date. If it asks for a username, they will type a string. But what happens if an attacker inputs 10,000 letter A's into that username field? What if they upload a compiled executable when the program is expecting a plain text file? What if they intentionally input a negative number for an array index? Humans are bad at anticipating every single way a user might break their code. Manual testing usually only checks the happy path, or the handful of edge cases the developer actually remembered to handle. Fuzzing is the automated solution to this problem. It's a testing technique where a separate program, the fuzzer, feeds the target software invalid, unexpected, or completely random data. The fuzzer throws garbage at the program as fast as it can physically can, sometimes executing thousands of times per second. While it generates and feeds this data, the fuzzer monitors the target's program execution state. It waits for the program to crash, freeze in an infinite loop, or trigger a memory violation like a segmentation fault. If the program crashes, the fuzzer logs that specific piece of input data so the developer can reproduce the crash and patch the vulnerability. There's a major problem with purely random fuzzing. Random guessing is incredibly slow and inefficient for complex software. Let's say a program has a simple check right at the beginning. If password equals admin, the string admin, then grant access. A fuzzer guessing completely randomly, byte by byte, will take an impossibly long time to randomly generate the exact string admin. It will just keep failing at the very first check over and over again, never testing the actual core code hidden behind it. To solve this, the modern security tools use coverage-guided gray box fuzzing. This is the industry standard today, used by popular tools like AFL and libfuzzer. Gray box means that the fuzzer has some visibility into the internal structure of the program it's testing. This relies heavily on compiler instrumentation. When you compile the target source code using a modified compiler like LLVM, the compiler injects tiny bits of tracking code into the program. Specifically, it inserts tracking instructions at the start of every basic block or control flow edge within the abstract syntax tree. Because of this injected code, the fuzzer knows exactly which lines of code get executed by a specific input. This is called tracking code coverage. It usually stores this in a shared memory bitmap. The feedback loop works like this. The fuzzer starts with an input seed, like the word hello. It feeds it to the program and watches the coverage bitmap to see what paths light up. Then it mutates the input slightly, maybe changing hello to cello. If that A happens to match the first letter of admin and triggers a new path in the branch code, Fuzzer also realizes that the mutation was valuable. It saves cello to a queue and then starts mutating that specific input to see if it can get even further. It actively rewards itself for exploring deeper into the program. Fuzzing algorithms are constantly evolving. Security researchers frequently publish papers claiming they have built a smarter, faster fuzzer. But this creates a logistical problem. If we have two different fuzzers, how do we scientifically prove which one's underlying algorithm is actually better? We need benchmarks. Historically, the security and academic communities test new fuzzers against massive real-world programs. They use benchmark suites like Google's FuzzBench or LavaM. They will take a complex piece of software, like an open source PDF reader, or the media player like FFmpeg, or a networking library, and run both fuzzers against it for 24 hours straight. Then they look at the final scores. If fuzzer A found 10 unique crashes and covered 50% of the codebase, and fuzzer B found 2 crashes and covered 20% of the codebase, fuzzer A is declared the winner. But there's a massive flaw in this evaluation logic. Real-world problems are millions of lines with incredibly messy code, written by hundreds of different developers over many years. When fuzzer B fails to get a high score, we do not know why it failed. What exact obstacle stopped it? Did the mutation algorithm get stuck on a complicated while loop? Could it not figure out complex integer math equations? Was it blocked by a checksum validation? The current evaluation method only gives us the final score. It provides outcome-based metrics. This tells us who won the race, but it gives developers absolutely no insight into what specific obstacles caused the loser to get stuck. This lack of detailed feedback is the exact problems the author of this paper set out to solve. Debugging complex systems is notoriously difficult because there is simply too much noise. If a program has 10,000 functions, isolating the one function causing a problem takes immense effort. Fuzzer developers face this exact problem when trying to improve their testing tools. If we want to build better automated security tools, developers need to know exactly what micro-level C language features make their tools fail. They need diagnostic benchmarks, not just final exams. They need a testing environment that isolates specific coding hurdles. If a developer needs to be able to confidently say, my fuzzer is highly efficient at navigating nested if statements, but its mutation engine completely breaks down when it encounters a 32 unsigned integer comparison. The paper points out that almost none of the standard benchmarks used in academia today provide this level of granularity. When they evaluate the macro-level performance while completely ignoring the micro-level features that dictate how the fuzzer actually navigates the code. When you look at the code at the macro level, you're just guessing at what needs to be improved. To solve this diagnostic problem, the authors introduce a framework called FeatureBench. FeatureBench is a benchmarking framework that takes a completely different approach from things like FuzzBench. Instead of pulling massive, messy, real-world applications from GitHub to use as targets, FeatureBench actually generates its own test programs from scratch. It generates synthetic, highly controlled C programs. These generated programs do not do anything useful. They don't parse files or process network packets. They are simply empty vessels designed to execute very specific patterns of logic. It operates as a clean room laboratory environment. Because the framework generates the code dynamically, the authors have complete control over the abstract syntax tree of the resulting program. They can adjust parameters in their framework to output a tiny 50-line C program that contains exactly one specific obstacle for a fuzzer to overcome. If a fuzzer gets stuck on a specific synthetic program, the developer knows with absolute certainty what code feature defeated their tool. There is no noise from other functions or complex data structures. It provides a pure, isolated test of the fuzzer's underlying path discovery algorithm. If the goal is to generate synthetic programs to test fuzzers, what exactly should be put into them? The authors need a scientific basis for the obstacles they generated. They conducted a systematic literature interview, reading 25 recent peer-reviewed research papers on gray box fuzzing. Their goal was to catalog what the academic community already acknowledges as major problems. From this review, they identified 7 specific program features that consistently block modern fuzzers. We can split these into control flow features and data flow features. Let's look at control flow first. One major roadblock is deeply nested conditionals. If a program has an if statement, inside another if statement, inside a third if statement, the fuzzer struggles due to path explosion. Mathematically, if you have 10 nested binary branches, you have 2 to the power of 10 possible paths. The probability of randomly mutating an input to satisfy all specific logical conditions simultaneously is astronomically low. Furthermore, a mutation that helps the input pass the second check might alter the data enough that it now fails the first check. Another feature is complex loops. Fuzzers notoriously struggle with while or for loops, where their number of iterations is dictated by the input data itself. If a fuzzer mutates an input that causes a loop to run 1 billion times, it completely tanks the execution speed, making the fuzzer incredibly slow. A third control flow feature is wide switch statements. Unlike a simple if-else block, a switch statement might have 50 or 100 different valid cases. A standard mutational fuzzer has a very hard time randomly generating the exact integer values required to hit every single one of these sparse switch cases. Now, let's look at the data flow features they identified. These are often even harder for fuzzers to beat than flow control. The most famous roadblock in fuzzing is called magic bytes. This is a hard-code string or integer comparison. Think about a standard file format, like a PNG image. A PNG file always starts with a highly specific sequence of 8 bytes. If an image parser's code requires these exact 8 bytes to be perfect before it proceeds to the rest of the file, a fuzzer will get completely stuck. Randomly guessing 8 specific bytes means guessing one correct combination out of over 18 quintillion possibilities. The fuzzer hits a mathematical brick wall and can't get past line 1. Another massive data flow issue is checksums. Many network protocols or file formats have a CRC32 or MD5 hash at the end of the data to verify integrity. The code will calculate the hash of the payload and compare it to the hash provided in the header. If a fuzzer mutates the payload to try and find a bug, the payload's hash will completely change. The program will then reject the input because checksums no longer match. The fuzzer doesn't understand cryptography, so it can't figure out how to update the checksum to match its mutated payload. Finally, they identified flow point math as a feature. Fuzzers are generally considered to mutate integers and bit flip standard byte arrays. When a program takes an input, casts it to a float, and prefers complex decimal division or multiplication before a branch comparison, standard mutational fuzzers completely lose track of the state and fail to satisfy the branch. Once they isolated these 7 made roadblocks, they engineered the feature bench code generator. They took these features and mapped them to 10 adjustable parameters. These parameters are the core mechanism of how the benchmark scales difficulty. Looking again at nested if statements, the parameter for that feature is depth. A researcher can tell if a generator is set to the depth parameter to 2, and it outputs a C program with 2 nested if statements. They can increase the difficulty by setting the depth to 15, generating a program with 15 nested if statements, testing the absolute limits of the fuzzer's path-solving capabilities. For a switch statement feature, the parameter is width. How many different case statements exist in a block? For the magic bytes feature, The parameter is the byte length of the string it has to guess. A 2-byte string is computationally easy to guess. A 16-byte string is practically impossible for a standard fuzzer without specialized techniques. By automatically iterating these 10 parameters through different combinations and difficulty scales, the Feature Bench framework generated a final suite of 153 distinct C programs. This suite is the actual benchmark. It's an organized gauntlet of 153 highly specific tests. Program 1 evaluates shallow loops. Program 50 evaluates deep loops. Program 100 evaluates a 4-byte magic string comparison. The authors use standard Clang and LLVM compiler toolchains to build these so they reflect real compilation data. It provides developers with incredibly granular, isolated data. A theoretical benchmark is completely useless if it's not tested to ensure it actually reveals insights that traditional benchmarks hide. The authors generated 11 different state-of-the-art fuzzers to evaluate using FeatureBench. They didn't just pick random ones. They picked fuzzers that represent entirely different approaches to the problem. First, they included standard mutational func fuzzers like AFL, AFL++, and libfuzzer. These just use basic bit flipping heuristics. They also included tools like mopt, which tries to optimize the scheduling of these mutations. But then, they included much more complex academic tools. For example, they tested Angora. Angora uses something called taint tracking. Instead of just randomly mutating bytes, Angora tracks exactly which type of byte of the input data flows into which specific if statement constraint. It tries to solve the constraint directly. They also used QSYM. QSYM isn't really a fuzzer. It's a concolic execution engine. It uses symbolic execution to represent inputs as algebraic variables, and then uses an SMT solver, like Z3, to mathematically solve for the exact input needed to pass a magic byte, check, or a complex nested branch. They ran all 11 of these tools against the 153 generated programs. Because fuzzing relies on random heuristics, they ran every fuzzer against every program multiple times, for 24 hours per run, to gather a statistically significant average. They measured exactly how fast each tool solved each specific parameter. The data from the evaluation proved their core argument. We desperately need better, more diagnostic benchmarks. The results showed that fuzzers that appear highly effective on real-world macro-level benchmarks often completely fail on specific feature bench tests. The overall high scores on traditional benchmarks were masking severe micro-level algorithmic failures. Let's look at the exact differences between the methodologies I just mentioned. As expected, standard tools like AFL completely failed the magic byte tests once the parameter length exceeded 4 bytes. However, QSYM, the symbolic execution tool, solved the magic byte test instantly. It just mathematically solved for the string. But when they tested complex input-dependent loops, the results flipped. AFL handled the loops just fine. QSYM completely choked and timed out. Why? Because symbolic execution suffers from state explosion when trying to unroll loops mathematically. More importantly, FeatureBench revealed significant regressions in newer tools that claim to be direct upgrades over older ones. A tool might optimize its mutation engine to solve deeply nested branches faster, but the data provided that this optimization actually broke its ability to solve wide switch statements. Because traditional benchmarks only provide a final overall score, developers frequently fail to notice they broke one feature while optimizing another. This is the primary contribution of the paper. They didn't build a new fuzzer to find bugs in software. They built a diagnostic framework to help researchers find bugs in the logic of their fuzzers. It switches the methodology from outcome-based evaluation to diagnostic feature-based evaluation. Any objective analysis requires looking at the limitations of the proposed methodology. The authors acknowledges these flaws, and they are important to keep in mind. The most glaring limitation is that FeatureBench relies entirely on synthetic generated C code. Does a fuzzer's ability work to pass an isolated 50-line generated test translate perfectly to its ability to test a massive networking library or an operating system kernel? Usually it doesn't. Real-world software involves complex memory allocations, asynchronous threading, file system interactions, and cascading interactions between different functions. A clean synthetic code generator does not replicate the level of architectural complexity. A fuzzer might pass the isolated feature bench test, but still fail in the real world because it can't manage the program's broader state. Additionally, there is significant risk of overfitting, often referred to teaching to the test. If the security community adopts feature bench as the definitive grading rubric, developers will inevitably start hard-coding their algorithms specifically to task these exact 153 synthetic programs, optimizing for the benchmark rather than the unpredictable reality of actual vulnerabilities. To conclude, this paper successfully highlights a massive blind spot in how software engineering industry evaluates automated testing tools. By moving forward toward targeted synthetic benchmarking, Feature Bench allows tool developers to open the black box and clearly identify exactly which code structures are defeating their algorithms. By moving towards a diagnostic approach, it is a necessary step to eliminate guesswork and engineer smarter security tools. Thank you for watching this presentation.